General relativity tells us that space is curved, and therefore the universe can be in one of three different geometries: open, closed, or flat. Now, I can't draw pictures of three-dimensional curved universes very well, so here are pictures of two-dimensional curved universes. This is a closed universe, a surface of a sphere in 2 dimensions. But if we had a closed three-dimensional universe, it's very simple. It'd be very similar. If our universe was closed, if we looked far enough in that direction, we would see the back of our heads. Light would go around the universe. And an open universe would be infinite in spatial extent, as would a flat universe. And that sounds really nice, but it's irrelevant. The really important thing is, in a universe full of matter, a closed universe will expand and stop and then recollapse in a big bang, in a big crunch, the reverse of the Big Bang. An open universe will expand forever, and a flat universe will expand and slow down but never quite stop. And that's why we wanted to know which universe we live in. And as I say, that's why I wanted to learn about it, because once I knew which universe we lived in, I would know how the universe ended. Okay? And so, weighing the universe tells us what the curvature of the universe is, and that's why we want to weigh it. So here I want to just show you in the next few minutes how, in fact, some of the most remarkable developments in cosmology, and then tell you how they completely changed our picture of the universe so that we understand that the universe we live in is the worst of all possible universes to live in. Okay, just so you know where we're heading. This is a cluster of galaxies. Each dot in this picture is a galaxy. Again, amazing to think about. Remarkable. Every one of these galaxies contains hundreds of billions of stars, and perhaps civilizations, some civilizations that are mired in religious gunk, other civilizations that have moved beyond, and other civilizations that are long dead. Because this is about 3 billion light years away. 3 billion years ago is when that picture was taken, basically. Now, clusters of galaxies are the biggest bound objects in the universe, so if we could weigh them, we can weigh all the mass in the universe, and we can weigh them now. We can weigh them by using general relativity. Because in this picture is a remarkable phenomena that Einstein first predicted in 1937, though he said it would never be observed. He underestimated observers. If you look at this picture, you'll see these blue things, these weird blue things. That is a phenomenon that we now understand as gravitational lensing. Einstein told us that a mass will curve space around it. And he realized, therefore, if you had a big enough mass and you have a source of light behind that mass, the light can bend around that object and come back and be magnified, just like my glasses magnify things. Or, like a cut glass goblet, if you look through it, I see many images of this room. Mass can act like a lens and magnify things and split images, and that's precisely what we're seeing. All of these blue things are different images of a single galaxy located about 3 billion light years behind this cluster. Gravity is magnifying the image, it's distorting it and bending it. Remarkable. Truly remarkable. But because we understand general relativity, we can work backwards and figure out how much mass must be in that system and where it is in order to produce that image. We can weigh the system using general relativity. And when we do that, here's an inversion by Tony Tyson, who's now up in Davis. This is the system, and the spikes are where this is where the mass is in this system. The spikes are where the galaxies are. But you notice most of the mass in this whole system of clusters of galaxies is not where the galaxies are. It's between the galaxies. It's where nothing is shining. About 50 times as much mass in this system, and in all systems we can measure, comes from stuff that doesn't shine. And physicists, with their linguistic perspicacity, have called it dark matter. And we now understand that 90% of the mass of galaxies and clusters, including our own Milky Way galaxy, is made of stuff that doesn't shine. And that isn't maybe that exciting, because there's lots of things that don't shine. You don't shine if I turn the lights out. Well, those of you from Los Alamos might, but the rest of you don't. But so it could be snowballs or planets or boring stuff, but it can't be. Because for reasons I don't have time to explain, we know how many protons and neutrons there are in the universe. We can actually measure that. And there aren't enough to make up all this dark matter. So we are pretty convinced that dark matter is a new type of elementary particle. Something that doesn't normally exist on Earth. And the great thing about that is that means the dark matter isn't just out there, it's in this room. As you doze off, it's early in the morning during this lecture. It's going right through your body. And that means we can do experiments here on Earth to look for it, which is remarkable. And in fact, I'll show you an experiment in a second. But By measuring the mass of these systems and this dark matter, taking normal matter plus dark matter and weighing it, we now have determined how much stuff there is in the universe. When physicists have an important number, they give it a Greek letter all the time. So we call it omega. Omega is the ratio of the total amount of stuff we know is in the universe divided by the amount of stuff you need to make a flat universe, the boundary between an open and closed universe. If it's less than 1, the universe is open. If it's greater than 1, the universe is closed. And we have now measured unambiguously that there's only 30% of the amount of material in the universe, including dark matter, to make the universe flat. Okay, we'll come back to that in a second, but I just want to show you that we actually do things in physics. This is an experiment to look for dark matter. It's a boule of germanium. And there are experiments like this all around the world, in mines, deep underground, because you want to shield out cosmic rays, because there are lots of them going through your body right now. You want to only see the dark matter, and the dark matter particles on average will go right through the Earth, we think, because they don't interact strongly. And most of the time right through this detector, but every now and then one of them will bounce off an atom, the nucleus of an atom of germanium. Heating, and the first thing we do is we cool this thing down to 1/1000th of a degree above absolute zero, which can easily be done nowadays. And if one of these dark matter particles bounces off a nucleus of an atom, it'll heat the whole thing up by 1/1000th of a degree. And we can measure that. And there are experiments here in South Dakota and in Europe, all over the world, looking for dark matter. We haven't found it yet. The other exciting possibility, which I should really indicate, which is one of the reasons people are very excited this year, is we may not have to wait for the universe to give us dark matter. The Large Hadron Collider, which is turning on this next month in Geneva, before it creates a black hole that will kill us all, we think actually might, by recreating the early conditions of the early universe, create the very particles which were last created at the beginning of time. So we may first see the dark matter by creating it in Geneva. It's a race. Okay, but to go back to this number here, this is a real problematic number. We now know the universe has only 1/3 the amount of matter to make it flat. The problem is that theorists like me knew the answer. The universe must be flat. Why? Well, there are two reasons. There's the one I normally say, which is it's the only mathematically beautiful universe, which is true. But there's another reason I don't usually talk about, but I'll talk about here. It turns out that in a flat universe, the total energy of the universe is precisely zero, because gravity can have negative energy. So the negative energy of gravity balances out the positive energy of matter. What's so beautiful about a universe with total energy zero? Well, only such a universe can begin from nothing. And that is remarkable, because the laws of physics allow a universe to begin from nothing. You don't need a deity. You have nothing, zero total energy, and quantum fluctuations can produce a universe. So if the universe isn't flat, we're worried, because then you've got energy at the very beginning of time. So that was another reason that people like me were pretty sure the universe was flat. But the damn observers came up with the wrong number. Well, this is a really crummy way to measure the curvature of the universe. Why don't we measure it using geometry directly? So we can measure the curvature of the universe. And to do that, I want to ask you, how would you measure the curvature of the Earth if you couldn't go outside the Earth and see it from a satellite, or you couldn't go around it? Very simple. You draw a triangle, and you ask a European high school student, what's the sum of the angles in a triangle? And we'll tell you 180 degrees, but he said, that's fine, you learned your geometry from Euclid. But on a curved surface, it's very different. On the surface of the Earth, I can draw a triangle that's very different. I can go along the equator, I can make a right angle, go up to the North Pole, make another right angle, and come back to the equator, and I have a triangle with 3 right angles. 3 times 90 is 270. So if I made a big enough triangle on the surface of the Earth, I could measure the curvature of the Earth. I wouldn't have to go around it. Now it turns out, even though this is a 2-dimensional picture, the same is true for a 3-dimensional curved universe. If I had a big enough triangle, and I measured the angles in the triangle, I could measure the curvature of space. And we've been able in the last decade to find a big enough triangle. And I want to spend 5 minutes telling you about that, because it's the most important, probably, observation in all of cosmology. The observation of the cosmic microwave background radiation, the afterglow of the Big Bang. One of the many reasons we know the Big Bang actually happened. What do we do? When we look out at space, we look at galaxies that were, say, 1 billion light years away and they're 1 billion years ago. But if we know that the universe is 14 or 13.72 billion years old, if we look far enough, we should see the Big Bang. Right? Well, we can't see all the way to the Big Bang. Because between us and the Big Bang, there's a wall. So like this wall here. Not really hard like that, but the fact the wall is opaque means I can't see past it. If I go looking back in the universe, it was getting hotter and hotter and hotter, and at a time when it was 100,000 years old, the temperature of the universe was 3,000 degrees. Slightly warmer than Phoenix this week. And at that temperature, the radiation is hot enough to break apart atoms, hydrogen in particular, and break it apart so the protons and electrons are separated. You have a charged plasma, and a plasma is opaque to radiation. So we can't see back past this time, simply because the universe is opaque. But that's okay. The reason I can see that wall is that light bounces from those lights there off the atoms on the surface of that wall, is re-radiated, but the air is transparent so I can see all the way to the wall. If we run this film forward, as the universe is opaque, 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 and then it becomes neutral, the atoms, protons capture electrons, neutral matter is transparent to radiation like this, and that means I can see all the way back to that radiation coming at that surface. A prediction of the Big Bang is there should be radiation coming at me from all directions, coming from that surface called the last scattering surface. It was 3,000 degrees then, it's 3 degrees now, and it was the radiation that was discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. And they won the Nobel Prize anyway. Because they discovered the afterglow of the Big Bang. Actually, another aside, I can't help this because this is amazing, and if you ever want to convince skeptics, you won't ever convince people of this who don't believe it anyway, but you've all seen this radiation. At least those of you who are old enough to be as old as me, before cable TV. Remember when the TV stations used to end? And then there'd be static? 1% of the static on your TV screen is radiation from the cosmic microwave background. So you've all seen it. Okay? But it's amazing we didn't even know about it until 1965. Okay? In fact, it had been predicted by people like George Gamow, but people have forgotten that. In any case, as interesting as that history is, on this surface is a very important scale, 1 degree. Why 1 degree? Because that represents a distance of 100,000 light years. Now, the surface existed when the universe was 100,000 years old. And Einstein tells us no information can propagate faster than light. So that means nothing that happened over here at that time could ever affect anything that happens over here. But more importantly, if I have a lump of matter that's this big, it knows it's a lump of matter, so it starts to collapse. But if I have a lump of matter that's this big across at that time, it doesn't even know it's a lump, because gravity can't have traveled across it. So it's like Wile E. Coyote in those cartoons when he goes off the cliff. He waits a while before he collapses. Okay? And such large lumps won't collapse. So the biggest lumps that can have collapsed at that time will be 1 degree across. And that gives us a cosmic triangle. Because we have a ruler that's 100,000 light years across, the size of the largest lumps, a known distance away from us, and in a flat universe, light rays travel in straight lines, and we can calculate the angle on our eye subtended by a 100,000 light year across ruler at that distance. It's 1 degree. In an open universe, light rays diverge as you go back in time, and the whole thing might be half a degree. The ruler will look smaller. In a closed universe, light rays converge as you go back in time. The ruler will look bigger. So we just have to look at that microwave surface, try and measure the lumps, and see how they 1 degree, half a degree, or 2 degrees. We've been able to do that in the last decade. This was the first experiment that did it. It was called the boomerang experiment in Antarctica. It was a balloon took this microwave radiometer above the Earth's surface to look at this radiation, take a picture of it, and this balloon went around the world, which is easy to do in Antarctica, okay? And it took a picture. It's really easy in the South Pole. You just do this. But anyway, and this is the image. Well, this is a false color image of that. I put it, superimposed it on the original image. This is the image of the microwave background, the hot spots and cold spots of the microwave background. And these are the lumps in the early universe. And the question is, how big are they? And here's a different false color image of the same region. And we can compare this with universes we create on computers. Here's a closed universe where the lumps are bigger. They should be this big across. They're 100,000 light years across. They should look that big. Well, that's bigger than these lumps. Here's an open universe, and you can't see the resolution of the screen isn't that good, but the average size lump is about that big. Smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, it's right now, we know, to an accuracy of better than 1%. The universe is flat. It has zero total energy, and it could have begun from nothing. And I've written a piece, although of course I got a lot of hate mail, saying that in my mind this answers this crazy question that religious people always keep throwing out, which is, why is there something rather than nothing? The answer is there had to be. If you have nothing in quantum mechanics, you'll always get something. It's that simple. It doesn't convince any of those people, but it's true. Now, great, we know the universe is flat. But if you've been awake, you realize 10 minutes ago I proved the universe was open. There's only 30% of the stuff in the universe needed to make it flat. Where's that other 70%? Well, if you put energy in empty space, so empty space weighs something, you wouldn't see it. It's the empty space between the galaxies. You're far away from the galaxies, you wouldn't see it. But what would that empty space do if you put energy in it? Well, it produces a cosmological constant. That would cause the expansion of the universe not to slow down over time, as any sensible universe should do, but to speed up over time. In 1998, people measuring these supernovae at large distances to measure the Hubble diagram tried to see what was happening at large distances to see if the universe was slowing. Well, they all knew the universe was slowing down. They wanted to measure how much. This doesn't look like much, but it was a revolution in cosmology. I can draw a straight line through that data set there and bring the whole thing down and make it horizontal. And if the universe was slowing down, these distant supernovae should have followed this curve. Much to the surprise of the observers, the supernovae lay above the straight line. And the only way to explain this, well, there's two ways. Either the data is wrong, which it usually is, or the universe is accelerating, speeding up. And if just for fun one believed it was speeding up and asked how much energy would you have to put in empty space to make it speed up by the amount we measure it, it's exactly the amount we are missing. Everything holds together. Our new picture of cosmology is that we live in a universe dominated by nothing. The largest energy in the universe, 70% of the energy in the universe, resides in empty space. And we don't have the slightest idea why it's there. Now, that's what I just said. Let me also put an aside before I get on to the rest in the last 5 minutes of the talk. This completes, in some sense, the ultimate Copernican principle. Copernicus told us we didn't live in any place special. We now know two things. Well, one thing. I'll tell you the second one in a second. This tells us that we are more insignificant than we ever imagined. If you take the universe, everything we see, stars and galaxies and clusters, everything we see, if you get rid of it, the universe is essentially the same. We constitute a 1% bit of pollution in a universe that's 30% dark matter and 70% dark energy. We are completely irrelevant. Why such a universe in which we're so irrelevant would be made for us is beyond me. Okay, good. I want a little bit of applause. Now we can go back to the science. What I really want to spend in the last few minutes is telling you is how it's changed our picture of the future. In science and the picture of the universe. It has changed our picture of the future completely. And I'm going to rush through this, so let me give you the short answer first. Kurt Vonnegut is claimed as having said this at a private girls' school when he gave a commencement address. I've given 2 commencement addresses, and I've never had the guts to say it, but I'd love to. He said, things are going to get unimaginably worse, and they're never, ever going to get better again. This was before the Bush administration, too, in fact. But that's our understanding of the universe. I want to tell you about it briefly. I want to tell you about a few things that you'll hear about, and some of the things that creationists and intelligent design people promote as arguing somehow that there's design in the universe.